Okay, so it's 5 past, so I'm going to make a quick introduction now. So I'd just like to welcome everybody here today. This is the third online session of the CGU 2020. As you all know, unfortunately, we're doing this online this year because, of course, it would have been in Banff. And if you didn't know, we will be holding the meeting next year in Banff. So we'll be looking forward to that. So before we start, I'd just like to thank everybody for joining, especially the 5 speakers that we have today, and remind everybody that the CGU is an organization that's here for you. It's a community organization. So if you are not members, it would be great if you could join. And if you are members and haven't paid your subscription, it would be great if you could do that. We recently had the AGM, and I'm now the president of the Hydrology section, which is a great honor. And I will be open to all members to make suggestions about how the organization could function best for all of us. And we'll be looking in the next little period at ways that we can come up with ideas to do more community events. It's already a really good organization for students. So if you're a student, you should try and get involved as much as you can. And we have awards every year that are available to students, very prestigious. Okay, so today we have 5 speakers, and most of them are on the theme of cold regions hydrology. So I'm not going to belabor it. I will introduce the first speaker. It is Sama Khawaja, I hope I have that right, from the University of Calgary. And she's going to be talking to us today about hydrological processes in frozen soils. Oh, and sorry, just before I do hand over Sama, just to say we'll have a 10 to 15 minute talks followed by a Q&A session. If you have a question, could you please write it in the Q&A box and not in the chat box? And I will then relay the question to the speakers. Okay, so thank you very much. Without any further ado, I'll hand over to you, Sama.
Yeah, sure. Thank you so much. It is definitely an honor to be the first one to go. I'm not going to lie, it's a little intimidating as well, but it just means I get the nerves out early and get to enjoy everyone else's presentation afterwards. All right, let's get this show going. All right, as you know, my name is Sama Khawaja, and today I'll be presenting the field results for my studies on frozen prairie soils. I wanted to give a bit of a background on the hydrological system over here. Unlike most, where water tends to run off into the rivers and streams, the prairies have a bit of a hilly landscape formed from past glaciers. So it's left these uplands and depressions. So any water that lands on this landscape tends to drain off into these depressions and then infiltrate down to the water table. This is what we call depression-focused recharge. So a lot of studies on these prairies have been focused on understanding the runoff and infiltration processes during spring, since most of our recharge comes from snowmelt. However, during that time, at least the first meter of soil is frozen. So one way we've explained that it bypasses this is through macropores. So what exactly are macropores? They're these large continuous openings that run through the soil. They're generally larger than the pore spaces between the sediment grains. They're formed from plant roots, which is one of the most common ways, frost heave, soil plowing, and cattle grazing. So what's happened is that during the winter, when the soil is freezing, some of these macropores are left dry. And then come spring, snowmelt infiltrates them on the upland. And once those are blocked, the rest of the snow runs off and collects in the depression where it infiltrates down to the water table. However, there's still some uncertainties on under what conditions do these happen and when does it transition from infiltration to runoff. An interesting event that happened on my site last year was that even though all the snow had disappeared from the landscape, the pond in the depression was still rising. And then this raised the question that if our groundwater recharge is not coming from snowmelt, what's the other source? So although these are small scale events, they're important in understanding more of the large scale events like the groundwater recharge, and that can help make the prediction of our conceptual models better. Looking at it on a larger scale, as climate change starts becoming a bigger issue, we have to understand how is it affecting our colder regions and changing their hydrological systems. Based on that, the goal of my research project was to shed some light on these frozen soil processes and see when does the transition from that infiltration to runoff, and see what role do macropores play in that. In terms of my site, I wanted to see whether I would see that delay in pond level rise as well. I decided to do this by applying a tracer on my field site during spring melt. In order to capture the spatial variability, I applied tracers on my upland and some close to my depression. As an accompaniment, I'm also doing some lab experiments on soil cores that were taken from my field site. I will go into them a bit more detail towards the end of my presentation. Going into my field site, it's located in Alberta. It's about 100 kilometers northeast of Calgary. Our climate is fairly dry. We only get about 400 to 500 millimeters of rain. We have very, very cold winters. That -30 that we talk about is not a lie. We have fairly dry and hot summers. My field site is a natural prairie grassland. It's mostly just used for cattle grazing. We have a number of potholes on this field site, but the one I was interested in studying is the Western Depression. On my map, I've outlined its watershed, which is about 200 meters in length and about 80 meters in width. The highest point from the depression is about 3 meters. On the right-hand side, I provided pictures of what my field site looks like in the summer and what it looks like in the winter. On the main map, you'll see that I've marked out a red line and a yellow line. The red line represents my depression tracer, and the yellow one represents my upland tracer. On the slide on the left, I provided a schematic of the dimensions of my tracers. Note that it's not drawn to scale, but it's just to give you an idea of where it's located from the depression. So the tracers that I decided to use are 2,5 and 2,6 difluorobenzoic acids, or DFBAs. They come from a family of tracers that have been used in hydrological studies, and they've mostly been reported to be conservative and detectable at low concentration levels. The way I prepared it is that I mixed 500 grams of each tracer in 100 liters of water, and then I applied them on snow lines with watering cans. Once spring started, I monitored my depression, and once it started ponding, I started collecting water samples, and I've indicated the locations on the schematic on the left. Once all the water had infiltrated and the ground had thawed, I went out and collected soil samples as well. I analyzed all my samples to find any signs of my tracer. In the following slides, I will present the results I have so far. So if you'll remember, I said I wanted to try and capture that delay in pond level rise. I did that by taking pictures of the snow cover, and I provided a couple of pictures at the top over here. I also measured the pond levels by hand, as well as taking data from a mini troll and a snow gauge in that depression. Drawing your attention to the graph, you'll notice that the pond level is offset by about 20 centimeters. And that's because during the winter, there was a warm spell that melted some snow that collected in the depression, forming that 20 centimeter layer thick, 20 centimeter ice layer. And so all pond levels were offset by that thickness. Looking at the graph, you'll see that air temperature had warmed by March 13th. However, my ponding didn't start until March 20th. March 25th was the day that I marked that there was complete snow cover depletion, and you'll see that in the third picture at the top. If that was the case, then I should have seen my pond level rising after that. However, looking at my pond levels, it looked like it had reached its max level before that date and was already starting to infiltrate. So unfortunately, I did not capture that pond level rise. However, you'll notice that most of the activity is happening while the ground is partially frozen. By partially frozen, I mean that within that meter depth, all the soil temperature sensors were reading 0 degrees or below that. The ground is considered completely thawed when all the temperature sensors are reading above 0 degrees. This activity has been related to macropores. And if we look at the soil temperature probes and the moisture probes from last year, they'll show that there's a lot of activity below that frozen layer depth. In order to better understand just how active the macropores are, I decided to do a snow melt water balance. And I provided that as a bar graph on the right over here. I got my snow water equivalent from snow surveys, and that was estimated to be about 41 millimeters. The way I got my runoff is that I took the max pond volume and divided that by the catchment area. And this gave me about 17 millimeters. Vapor flux is not very active on my site, so I didn't account it for much. So that meant that majority of it, at least 22 to 23 millimeters of it, had infiltrated into the soil. If I do a quick calculation from that, it turns out that only 44% of my snow melt had ended up in my depression, well, almost 66% had infiltrated. This kind of gives me an idea that depending on how dry these macropores are, they can actually take a huge chunk of the snowmelt that could have gone towards groundwater recharge. Looking at this, that would mean that my tracer would show a similar activity, which it kind of did. So the main melt period was between March 20th and March 23rd. This huge spike that we see in my depression tracer actually happened on March 20th. It is a little misleading, and that's because the pond had unfortunately not completely thawed, so I could not take a lot of water samples, hence I saw such a huge concentration. What you'll notice looking at the rest of the days, as the pond thawed and more melt collected in it, and the ground also started to thaw, the tracer reached stable levels and eventually started to decrease along with the pond levels. We see a similar trend with my upland tracer. The spike is slightly smaller, and that has to do with the fact that of its distance from the depression itself. Overall, about 50 to 60% of my tracer had arrived in my depression. A majority of it seemed to have happened right in the beginning of snowmelt. This was during the time that the ground was still frozen, and also there was still snow on the ground. So the likelihood of it arriving by runoff was fairly slim. Remembering those air-filled macropores, they're also connected laterally. So perhaps that this amount of tracer, or at least some amount of snowmelt, actually arrives in my pond through the subsurface and through these air-filled macropores. If that was the case, then the tracer that was not recovered should be in the soil. But looking at my soil samples, I realized that I couldn't find any signs of my tracers. And so the two possibilities I came up with is that these tracers are not as conservative as we think they are, and there might have been some degradation, or once the ground had thawed, whatever tracer was left in the soil had infiltrated down to the water table. So in conclusion, although I was not able to capture that delay in pond level rise, I did find out that depending on how dry these macropores are, they can actually cause a significant amount of infiltration during spring melt. Another thing I found out is that the amount of water that collects in the depression, which had once been attributed to just being from surface runoff, could in fact include a subsurface flow component. And if that does play a significant role, then it should be considered in future conceptual models of the prairies. And if we're trying to model and understand global warming effects, then it's even more important to consider it. I had mentioned that I was also doing lab experiments. These lab experiments are trying to understand how soil moisture conditions change during the winter, and how does it affect the soils during spring melt. What happens over here in the prairies is that these warm winds come in from the mountains, called Chinooks, and they warm up the air temperatures and cause snow to melt and infiltrate into the ground, and thus changing the dynamics of these macropores. I was going to try and mimic that with my soil cores and see what results I would get. And also, I decided to continue with my tracer applications, but I wanted to compare the difference of macropore activity between croplands and grasslands, since more and more of prairie grasslands are being converted to crops. It would be interesting to see how, as these lands are being converted, how they are changing the dynamics in the prairies. As the country slowly opens up from this pandemic, I'm slowly getting back into the lab to continue my experiments. And so hopefully I will have more results that I can present and show what I have. And with that, that brings me to the end of my presentation. Thank you for listening, and I will be taking any questions.
Excellent. Thank you very much, Sama. That was a very interesting talk. I would invite people to submit questions in the Q&A. And we have our first question from Nicholas Canar. I'm just going to read them out. Sama, you gave an interesting talk. How might you differentiate between water pathways associated with through flow and overland flow? Do you think that modeling might be able to separate the water pathways?
I can't say that I'm the best expert at modeling, but I do know that we've had PhD students that have modeled the prairies. And from their results, they seem to think that there's a certain amount of infiltration that happens in the beginning. I think that if there's any subsurface flow, I have a feeling it's probably right at the start of the spring melt. So if anything, it would be difficult, but I do think it can be possible for just considering that small window. I don't know if that answers the question.
Yeah, that's good. Others, please do ask questions. I'll take the liberty of asking you a quick question. So I think I missed, I didn't quite understand how you applied the tracer. Could you maybe repeat that? And also, can I ask you to explain how it is you know that that tracer that you've recovered in the pond didn't get there by surface runoff?
So if we're thinking about a general system of, I'll answer the first question since you asked how we applied it, how I applied it. So I mixed about 500 grams of them in water, and since there was still snow on the ground, I applied the tracers on with watering cans right on the snow lines. So hopefully that answers the first question. And then the second one you asked, how do we know it's not surface flow? Well, the ground was still fairly covered in, snow. I'll go back to the picture that I have if I can. So this huge this huge spike that we see happen on March 20th. And if you look on the picture over here, the ground is still fairly covered in snow. If you're thinking about general dynamics of how overland flow happens, if it is flowing perhaps under the snow, there's likely chance it did get frozen as well. Whereas if you look at the if you look in the subsurface, most of these macropores are dry, so it creates a lot of pathways for them to get there. Of course, there's like thermal activity that's happening that could have potentially frozen it, but this is the clear. This seems to be the more it seems to be the easier path to take than going overland.
Okay. I think it's very, very interesting what you're saying there. Anyway, yeah. There's another question coming in. So it's from Renato Pardo. Thank you, Renato. So he says, thank you very much for a great talk. I'm wondering what you make of the fate of the meltwater once it goes through the macropore. Why doesn't it refreeze?
It does. You also have to think about that there is the watershed has, it's pretty large. So there's a lot of water over there and there's only so much that those macropores can hold. There's a very good paper by, I believe her name is Apples. I think the paper came out in 2018. She gave a very good explanation of what happens to these macropores. And they basically, once they infiltrate, there's, depending on the thermal activity that happens, they can actually freeze very close to the surface, and that can actually cause runoff to happen much earlier.
Okay, excellent. I'll do one more question. This is from Jesse. Hi, Sama, great talk. Do you think soil swelling played a role in the dynamics you saw? Yes,
it does. I believe it does happen once the ground is completely thawed, and I will say that on my field site in particular, there's a lot of clay. So I do think swelling did play a part in the dynamics.
Okay. All right, thank you very much, Sama. That was excellent. So we better move on to our next speaker, who hopefully has got her audio sorted out. So this is Élise Devoie, I'll probably say that wrong, from Waterloo. Again, talking about hydrological processes in frozen soils.
Wonderful. Thanks so much. My name is Élise Devoie, and I'm a PhD student under the co-supervision of Professors James Craig and Bill Quinton. And today I'm going to be talking about efficient modeling of seasonal soil freeze-thaw. So this work started off with some field work that I completed at the Scotty Creek Research Station in the discontinuous permafrost region in the southern Northwest Territories. This field site is really unique in that it has really clear distinctions between areas that are underlain by permafrost and areas that are not. And the changes in permafrost coverage are happening really rapidly there, which kind of led me to the idea of trying to be able to make a numerical model that would represent those changes more efficiently. And so this work is just really an extension of that model. But over the past 5 decades or so at the Scotty Creek Research Station, we've seen a huge loss in area covered by permafrost, which you can see in gray in these figures here. And so being able to capture that change in the landscape is important because, well, in this landscape, as you lose permafrost, often you get the transfer from these elevated peat plateau areas that are able to support a tree canopy to surrounding wetland features. So we get landscape change. There are other things that happen due to frozen ground processes, which are important not just in describing a landscape, but also in representing the hydrology of that landscape. Some of the impacts of ground ice include changes to infiltration, as Sama just explained, how the presence and absence of ice can actually change the dynamics there. There's also moisture migration due to temperature gradients, not only pressure gradients. There's the concept of winter quiescence. So often, hydrologically speaking, large-scale models will assume that over the course of the winter, water kind of stops moving, especially in environments with permafrost, where this may not actually be the case if talic is present in the soil column, where that's a perennially thawed region, which is able to convey water year-round. Finally, relevant to this research site that I was looking at, soil destabilization may occur as the ground ice sort of helps to maintain that pore structure of the soil. And when that's lost, then it kind of sloughs off or subsides. So it's not that there are currently no models capable of representing freezing processes in soils. There are in fact two main categories of models that exist, which both have strengths and shortcomings. So first off, there are continuum models, which generally are non-equilibrium models, which can represent multiple freeze-thaw fronts. However, they're really numerically expensive and sometimes they're computationally unstable, which means that it's hard to run large-scale models or long-duration simulations, and scenario testing and sensitivity analysis is usually computationally prohibitive. In order to address these concerns, front tracking models also exist, and these are relatively efficient. However, they require steady forcings, and they track usually just one single freeze-thaw front, and they're kind of empirically based. So they don't have the ability to describe quite as wide sets of parameters. So what I want to do is to be able to develop a model that kind of fills the gap between these. So I want it to be a computationally efficient model that's semi-analytical in nature so that it can accomplish this task of being computationally efficient. It needs to solve a non-equilibrium problem, meaning that it can have variable forcing temperatures at the ground surface. It needs to be able to represent a variably saturated soil column with infiltration events. And the soil column needs to be able to be multi-layered, and it needs to do all of this while being computationally stable. So this model is hopefully going to describe seasonal frost, active layers, and permafrost. Now, if you saw me at the CGU talks last year, this may all kind of look like deja vu up until this point, because I have been working on this model up until now. And last year I presented the conditions for a stable permafrost situation, so one that did not include a talic. And so I sort of had a proof of concept. And so now what I'm going to do is extend those results to include the effects of seasonal frost and areas with a talic to show that this model is actually capable of filling this knowledge gap that I set out to fill. So first off, let's look a little bit at this environment. So I wanted to be able to, what I modeled previously was the case of an active layer that sits on top of that permafrost body, which I'm not sure if I'm pointing or not. Maybe I'm not. There we go. Now I am. Okay. So here we looked at this situation. What I now want to talk about is the presence of a talic. So this perennially thawed layer here, we can have that active layer that only freezes down to here and leaves this thawed layer on top of the permafrost. And there's also the case of wetlands or soils such as we have around here, where we have an active layer. Essentially, you shouldn't call it that because there's no permafrost underneath, but it's just this layer that freezes and thaws seasonally on top of a completely thawed soil profile. So this interface model, how does it work? How is it able to come up with all of these requirements? Well, first off, it's called an interface model because it's made up of a finite number of dynamic domain elements that are defined by soil properties. So what we're doing, instead of breaking up our soil column into hundreds, if not thousands of tiny little elements in a finite element model, we break it up into maybe 5 or 6 elements that have each different soil properties, and we allow the interfaces between these elements to move based on mass and energy transfer across them. So if we have infiltration happening, that will percolate downwards, hit the water table, and allow that interface of the water table to move upwards, and that movement changes the interface position and the size of the domain elements without changing the number of elements. Now, the mass balance is relatively simple. It's a near equilibrium solution to the unsaturated Richards relationship. And the more complicated and fun part of this is the energy balance, where the temperature profile is determined through the superposition of analytical solutions to the heat equation. So that's a big mouthful of math, essentially to say that it's possible to find a closed form solution to the heat equation for one time step or one temperature condition at the ground surface. And if we use this and extend it in time, we can add up, by breaking up time into these little time steps, we can add up those solutions through history of the soil profile, and that allows us to approximate the gradient at the interfaces. Regardless, what I want to show you is that it actually works. So these are the results for that stable permafrost column that I was initially testing the model out on. And here what we see is a contour plot that is generated by a finite element model. So that was one of those models with hundreds of tiny little boxes, and each box represents a temperature. So here we're looking at depth below the ground surface on our y-axis, time on the x. Dark blue represents a cold and completely frozen ground, and red is a warm, completely thawed ground. Now, the fun part here is that I'm looking at the performance of the interface model, which is shown in this white dotted line. And you can see that it lines up really nicely with that contour between 0 and negative 0.05 degrees, which is actually the freezing range that I assigned to the continuum model. So these results show that it's working really, really well in this condition. Now I wanted to be able to answer some more questions, be able to model slightly more complicated soil profiles. So then I moved on to the case of a soil profile with the talic, that perennially thawed layer. And here you can see that, again, we have the same contour plot results. Clearly the boundary conditions and initial conditions are somewhat different. And we do have this perennially thawed layer here. And again, the dotted line, that interface model, is tracking the interface between that 0 degree and negative 0.05 degrees really well. So again, we're able to capture the behavior or that freeze thaw behavior in the case of a talic. Another way of looking at this that is maybe a little bit easier and more quantitative is plotting the total ice content in the soil column. And I did this because in the continuum model, it's allowed to have a fractional ice content. So you can have like a slushy zone, which is kind of hard to interpret from a contour plot because that was just report temperature. So here we're looking at the total ice content between the interface and continuum model. And again, you see that they line up really, really effectively. Now, the really fun part about this is the efficiency of this interface model as compared to the continuum model. So here we're looking at saturated, unsaturated cases with and without a talic. And you can see that that finite volume or that finite element model that I'm talking about with the tiny little compartments performs much, much, much slower than the interface model for the same time step. And then what is really exciting is that we can actually increase this time step from a 1 hour time step, which is the largest time step that's possible for this finite volume method without it becoming numerically unstable. For the interface model, we can take it up to 1 day and we still get numerical stability, and we can also get really good representation of these results and pretty crazy speed ups in simulation time. The other really fun result is that we can change the size of our domain. So each of these simulations dealt with a 3-meter vertical soil column. Now I wanted to be able to see if it was sensitive to the distance to that bottom boundary condition. So I increased that to a 10-meter domain to get my finite volume method to run in almost 3 hours. But as you can see, the interface model didn't change in simulation time because it doesn't matter how big each one of the elements are. It just matters the total number of elements, and that stayed the same regardless of that increase in depth of that bottom element. So a lot of really exciting and fun things that seem to be going well with this model. Now, the last thing that I wanted to do was look at seasonal freeze thaw. And so permafrost is a very important component in cold region systems, but it isn't found everywhere. And seasonal freeze thaw happens in quite a large part of the world, as you can see from this map here. So in order to extend this model and make it more useful in different hydrologic applications, I wanted to be able to do a good job of representing this. So here I looked at 2 different scenarios. The first is near saturated peat, because all of the permafrost simulations that I've done are using field data collected at the Scotty Creek Research Station, which is a peatland. So I started off with a peatland. So here we can see the top plot looks at our saturation, and here dark blue is a completely saturated profile, and then as we go to the lighter blues we see partially saturated, and the water table position is that interface that we can see that the interface model, that white dotted line, tracks it really, really well. Again, I plotted up the total ice content comparing these two models, and they also track really well. And finally, we can see the results on that contour plot using the continuum model and the interface model to compare them. And again, the interface model seems to track perhaps not quite as well as in the permafrost case, but it does seem to do a decent job of capturing the position and especially the timing of that freeze and thaw process, which is probably more important when looking at hydrologic modeling. Now, the second scenario I tested was dry mineral soil, because if you kind of look out your window, wherever you are, that's more likely where you are. Not that many people live in peatlands, though I really love them. They're pretty full of bugs though, so maybe it's good they don't live in a peatland. Anyway, so looking at dry mineral soil, again, we can see that the water table position is really well represented by the interface model. And it even maybe does a better job of capturing the total ice content and tracking the position of that freeze thaw front in these mineral soil conditions. So all in all, it looks like the interface model is doing a really more than adequate job of capturing the freeze thaw behaviors. So how exactly can we use this? What is the real point of developing this model? Well, first, it allows us to track multiple freeze thaw fronts in a much more numerically stable way than the continuum models, which allows us to be able to do scenario testing, to do sensitivity analyses, to do really long time simulations, and it allows us to also represent partially unsaturated frozen soil, which is something that's lacking from a lot of models. And my hope is that this model can be integrated into a current hydrologic modeling framework to improve the representation of infiltration, hydraulic conductivity, thermal process properties, and mechanical properties in soils that are undergoing freeze thaw, to improve our ability to predict and represent hydrology, especially over winter in Canadian basins. So thank you so much for listening, and thanks to all the people who helped me do fieldwork and who contributed to model development. And if you have any questions, I'd be very happy to hear them now.
Thank you very much, Élise. So yes, we'll open for a couple of questions. We're a bit pressed for time now. So the first question comes from Ines, who says, thank you for your presentation. My question is, as one of your goals is to produce a non-equilibrium model, have you used a non-reversible approach to solve the thermodynamics of the system? Or what was the set of assumptions that you used to solve the thermodynamics during the freeze-thaw processes?
I hit the answer live button. I hope this works. So essentially, I'm not entirely sure I understand your question, but I will answer what I think I know. So here, the assumptions that I made when solving this problem, what were the assumption, well, first off, that the mass balance is near equilibrium, and I'm not solving the unsaturated Richards equation fully in each time step. And I assume that there's a finite temporal history of the soil profile. So the semi-analytic solution that I have essentially is, if I were to integrate it numerically with a very fine time step, it should give me an almost exact representation of the fluxes, but instead I assign it a time step and I integrate over the course of that time step to get an average value. But that also is an assumption, so I have to kind of discretize time. And in my discretization of space, I also have these assumptions, and I'm also breaking up the soil into these representative domain elements, which each have homogeneous soil properties. So that's another assumption that I'm making there, that say the thermal conductivity of the unsaturated layer has this distinctive equivalent value, which is based on the averaged water content of that particular layer. I'm not sure if that completely answers your question,
Well, I think that was a great stab. It might be something to talk about offline because we're a bit pressed for time. Two more quick ones. So Nicholas again, thanks for your talk. Can you comment on parameter sensitivity and how parameters affect model stability?
So I guess it's pretty great because this model is very, very stable. The issues that we can run into are the diffusivity. So if we have a certain combination of thermal conductivities and densities of different soil components, then sometimes it isn't a very good assumption to make really large time steps, but the model stability isn't affected. It's just the quality of the predictions. Also, if there's a really low hydraulic conductivity, the equilibrium assumption of that saturation also isn't a very good assumption. So the model very rarely crashes. However, you have to be sort of intelligent about what kind of information you put into it in order to get reasonable results.
Great. Right, one more question from Masaki Hayashi. Great presentation. Great to see such a good match between the continuum and the interface model, but the real challenge is to test against actual field data. Are you planning a model testing against field data?
So I actually already have done a model testing against field data. I didn't present it here because of time, etc. But it does seem to represent so I broke up the field data into cases with a talic, without a talic, and I forced with sort of simulated temperature boundary conditions drawn from field data, and they do fall within sort of the 25th percentile. And I plotted these up. I can send you some of these results. They're actually hopefully going to be published really soon, which show that there is in fact quite a good relationship between that field data and the model.
Excellent. I think a lot of us are looking forward to seeing your papers on this.
Wonderful.
So yes, thank you very much, Elise. We must press on. So I'll ask you to stop sharing your screen and we'll move now to Ela Mastej. I'm sure I've got that wrong. Who is from Wilfrid Laurier University and is going to be talking about permafrost.
My name is Ela Mastej, and I worked at Wilfrid Laurier University under the supervision of Dr. William Quinton. And today I would like to talk about the evolution of ground freezing methods at Scotty Creek and what we learned from it so far. Ground cooling technology has been around for quite a while, and it is a very effective method to stabilize ground temperatures and to support infrastructure in cold regions. However, it is a technology, it is predominantly, it's very application-oriented technology. So it has been predominantly used in mineral soils because that's where you want to build things. But climate change and increasing northern development is sort of changing that paradigm, and it drives the need for cost-effective and more easily deployable designs and more robust designs in diverse environments, so kind of expanding beyond those mineral soils. And Scotty Creek is a characteristic subarctic wetland, so it's a great place to actually study those systems. The Northwest Territories and Scotty Creek Basin are very affected by man-made disturbances. Those disturbances, the majority of them, the most widespread, are seismic lines, and they relate to resource exploration. And they're very, as you can see on the picture, they're very predominant, very prevailing in those environments. Just to put it in perspective with some numbers, the basin itself covers 152 square kilometers, and it is covered by about approximately 133 kilometers of seismic lines. And that is over 5 times the natural drainage density of the basin. So those seismic lines are implicated in the hydrology, and also, very importantly, they are very detrimental to permafrost. So there's pretty much, in that particular region, what we have seen, there is no recovery of permafrost under the seismic lines. And for this particular project, a stretch of about 400 meters of a seismic line was adopted for various parts of this investigation. So the objectives of of the study were to evaluate the performance of first of 3 cooling systems that were initially installed. We also wanted to look at the insulating role of snow on the ground thermal regime in that very saturated environment. And the third objective was to put those two things together, so to combine the single phase thermal siphon and snow excluding cone. And the fourth objective was to look at very novel designs of coaxial systems. So between 2013 and 2016, we had 2-phase thermal siphons installed. And on the right-hand side here, you can see the aerial view of that configuration. So there were 7 of them in total, and there were 2-phase systems. So what that means is that the interior of the pipe is filled up with, there's the liquid, and as the liquid draws heat from the ground, it starts evaporating. So now we have vapor phase present, and as it moves above the ground surface, it gives off the heat. It cools down and it condensates, and it falls back down, and it's the process is circular, and it happens spontaneously, so it doesn't require any pump or any additional energy source. In 2016, one of those initial thermal siphons was replaced by a different model, which was single-phase thermal siphon. So in this case, the interior of the pipe was filled up with a cooling liquid, so it was just one phase, and the same principle, the liquid draws the heat, and as it warms up, it changes density, so it starts moving up as it is less dense. Above the ground, it gives off the heat, and it becomes denser again and heavier, and it starts falling down. So again, spontaneous process. However, this time we installed the pump to increase the circulation of the liquid and to increase the efficiency of the heat transfer. In 2017, 3 additional thermal siphons of that original configuration were replaced with the single-phase thermal siphon. And here we have some results. So this is temperature time series for all 3 systems. So here we can see that that very initial configuration of 7, it didn't really yield any change. This would be a typical profile, ground thermal profile for this environment. So, so temperature at the depth between 2.2 to 2.4 meters below the ground surface remains at about 0. And we can see that when we installed single-phase thermal siphon, the following season, the following winter, the temperatures went down to 1 degree. And interestingly, they remained below 0 degrees the following summer. And again, the following year, 4 single-phase thermal siphons, so that increased configuration increased the heat transfer. So we concluded from that the 2-phase systems are just not efficient enough in peat-based substrates. So we have a lot of water, a lot of energy has to be removed, and the latent heat exchange within the thermal siphon itself is not efficient enough. Single-phase cooling systems are definitely more efficient, and multi-component configuration increases the amount of thermal gradients and therefore the amount of heat that is being removed. So the following year, we installed 4 individual snow shading cones along the seismic line. And that was the installation at the end of August 2018. So I'm representing here cone 1 and cone 2. So what happens over the winter season, there were 2 cones that were entirely snow covered and 2 that were partially snow covered. That was unintentional. However, kind of worked as a control for us. We got, over the winter season, we got our seasonal freeze of that top layer of the soil. And at the end of August 2019, at the time of maximum seasonal thaw, under the cone that was only partially snow covered, we had a frozen lens that was 15 centimeters thick, and it was 60 centimeters below the ground level. And there was none of that present at cone 1. In terms of results, we can see here that for cone 1, ground temperatures remained relatively stable. And here for cone 2, which was partially snow covered, temperatures were definitely responding to the air temperatures. In terms of actual numbers, the difference was very large. It was about a degree for the top layer and about 0.65 for the lower portion, so between 50 and 80 centimeters. So not a huge difference in terms of temperature. And that brings me to the point, this is a very important point, that evaluation of snow insulation, when we do that, we really must consider other thermal processes that could be reflected in that temperature. So the temperature itself is not a metric, it's not an ultimate metric to assess the insulation of snow. So we have to consider freeze thaw and moisture migration and those processes that could influence the temperature. So moving on to the next objective, the same year we put together, we took that single phase thermal siphon and we installed snow shading cone to see how that would work in that environment. So again, this is the installation at the end of August 2018. Again, we got our typical seasonal freeze of that top layer. And at the end of August 2019, so again, at the time of maximum thaw, we had frozen ground below 70 centimeters below the ground surface. So it wasn't just a lens, but actually the permafrost table moved up. And here we have the aerial views. So we have the thermal siphon, we have the cone, and this is actually the area of influence. Again, temperature time series reflect that we can see a downward trend despite some issues that we've encountered, such as snow insulation for part of the season and pump failure. But again, there is a downward trend, and snow was removed at the beginning of February, and we can see that temperatures plummeted to about -15. So reduction of snow cover around the thermal siphon increased the initial rate of heat transfer because of those vertical gradients that existed in the absence of snow. However, we definitely need more studies, possibly in the lab as well, to actually decouple those different gradients, the horizontal and the vertical. And in 2019, we installed very novel designs. So they were insulated and non-insulated coaxial designs, and they were passive, so they didn't require any external energy source. So again, we had a tube that, actually we had two tubes. So what happens here is we have cold liquid, and it starts moving down because it is heavy. And as it moves down, it starts forcing through the slots the warm liquid that is now warm because it absorbs the heat from the ground. So it starts moving up, replacing it. And so we have this very deliberate routing of the liquid, the cooling liquid within the thermal siphon. And we, here in the non-insulated design, what happens here is that we're losing some heat internally because we have a gradient between the cold liquid outside and the warm liquid. So we're losing some of the heat and some of the efficiency as well. And that is, we can see that clearly here in the results. So this is, again, temperature recorded about 2 days after the installation. So we can see here that at 150 centimeters below the ground level, the insulated thermal siphon has much lower temperature, about 4.5 degrees, and we have not quite -2 at the non-insulated one. However, we noticed that after 6 weeks, temperatures tend to converge. So the efficiency over a longer time scale could be comparable. But again, immediately after the installation, there is that noticeable variation, and this is due to that internal insulation of the inner tube. And that takes me to the conclusions. Thermal siphon technology definitely demonstrates considerable ground cooling capacity in peat-dominated environment. Single-phase systems are transferring heat more effectively than two-phase systems. So So definitely, this is the direction to take that development for sure. And coaxial thermal systems, they do not rely on any external energy source. So considering that, they demonstrate significant heat transfer efficiency as well. And very important point, when we evaluate the systems, we really must consider the initial conditions at the time of installation. And it would be great to move forward with establishing coefficient for each system, heat transfer coefficient or heat transfer characteristic curve, to be more consistent when comparing them. And thank you very much to everyone for your attention on a Friday afternoon.
Thank you very much, Ela. So I will again invite any questions, and we'll start with a question from Nicholas. Thank you, Nicholas. Thanks, Ela. How many of these systems should be installed over a basin to cause an appreciable reduction of permafrost thaw required for mitigation of impacts? Is there a rule of thumb relationship or design equation? What would be the overall cost?
Yeah, that's a great question, actually. I don't know the exact answer to that. Our studies right now are very sort of micro scale. When we decide where to put them, when to install the thermosiphons, it is very important to really understand ground thermal regime on a larger scale and identify those kind of, or I shouldn't use the word hotspots, but those important spots where lowering the temperature would make a difference in a larger scheme of things. So I think it's very complex. So I don't know the exact answer to that, but it's definitely, that question came up quite a few times. And having a model would be, of course, a great idea to aid answering that question.
Yeah, I guess it's probably fairly early days in the development of this technology. So
absolutely, yes.
I had a question. So you can see how these thermosiphons will essentially allow heat to leave the soils in the winter and hence cool them. But how come you don't get heating of the soils in the summer as well? And doesn't that kind of...
No, that's a great question. No, they deactivate during the summer, because what happens is, so during the summer, basically the warm air, sorry, the cold air sinks to the bottom, and because it's warmer outside, it doesn't take any, the liquid is not moving up. So basically they in a natural way, they deactivate when it's warm outside, yeah.
So it must be some very exotic liquid in there, is it?
No, it's not. It's actually antifreeze. It's glycol based. So it's actually fairly simple.
Okay. Well, thank you very much, Ela. I'm going to keep moving on because we're also running a little bit late at this point. So thank you very much, Ela. And we'll move on now to Hilary Smith, who is from the University of Northern British Columbia and the University de Quebec at Montreal. And she's going to be talking to us about the SPADE experiment.
Hi, everybody. I'm Hilary Smith, and I'm representing the SPADE project. So since there's no objections, I'm assuming people can hear me and see my presentation.
Yeah, looks great. Looks great.
Okay, good. Yeah, so my presentation is called Measurements and Preliminary Results from the Storms and Precipitation Across the Continental Divide Experiment, so SPADE. It's a collaboration between the University of Quebec at Montreal, University of Northern British Columbia, University of Manitoba, and the University of Saskatchewan. So I'll be going over the experiment and discussing some of our initial results. And so here's just some background information and the motivation for our project. The Continental Divide is oriented north-south along the Canadian Rockies, and you can see it here. It's this red dashed line. And it's a critical headwater for hydrological drainages to either the Pacific Ocean, the Arctic Ocean, or the Atlantic Ocean. Precipitation can occur on the western side of the divide with moisture coming from the Pacific, on the eastern side of the divide in upslope events with moisture coming from the prairies, or on both sides simultaneously. And so there have been some recent major flooding events along the Eastern Rockies and have been attributed to upslope flows. Most recently in June 2013, that caused catastrophic flooding in southern Alberta, BC, and notably flooded downtown Calgary. That was one of the costliest natural disasters in Canadian history. So the objective of our project is to investigate atmospheric conditions and precipitation distributions, including the amounts and types across the continental divide. So we conducted a field campaign last year from 24th of April to the 26th of June in 2019. And so we had 3 main field sites along the border of BC and Alberta in the Southern Rockies. We had Nipika Mountain Resort, which was located in a valley on the western side of the Continental Divide, and then Fortress Mountain Power Line, which was located midway up a mountain on the eastern side of the divide, and Fortress Junction Service, which was located at the base of that mountain on the eastern side of the divide. We also had 2 temporary field sites, Storm Mountain Lodge, which was located just east of the Continental Divide, and then the U of Calgary Biogeoscience Institute. For the purposes of this presentation, we'll just be talking about the 3 main field sites. So here we have our typical instrumentation setup. This picture is from Fortress Junction Service. So we had standard meteorological instruments to measure air temperature, air pressure, wind direction, wind speed, etc. We had a Doppler LiDAR, which is just here, and that measured the local flow field prior to precipitation. We had a micro rain radar right here. And so that measures the amount of condensate aloft, as well as the vertical motion of particles, an optical distrometer, which diagnoses a precipitation type. And then we had a pluvio or a GNR, depending on the field site, for precipitation measurements. Something to note is we did not have a LiDAR at our Nipika field site due to power constraints. We also had manual observations and microphotography. So we had observers on site at Nipika Mountain Resort and Fortress Mountain Power Line whenever there was precipitation occurring. So for example, if there was precipitation at Fortress Power Line, we also had observers at Nipika, regardless of whether there was precipitation occurring at Nipika or not. And so for the manual observations, we gathered data about the precipitation phase and particle type. And we also took microphotographs of snow particles. The majority of our microphotography images are from Fortress Power Line, and that was due to a lack of solid precipitation at Nipika, as well as warm temperatures. And so here's a weather overview of the entire field campaign. The top panel is Nipika, and the bottom panel is Fortress Power Line. And the red line indicates air temperature. So you can see that temperature was much more variable at Nipika than it was at Fortress Power Line. And that's likely due to increased cloud cover at Fortress Power Line. And then the bars represent the amount of precipitation. So blue is for snow, red is for mixed, and green is for rain. So you can see here, Fortress Power Line received much more precipitation than Nipika, and it received a variety of precipitation, whereas Nipika received mainly rain. And then the gray sections that you can see here, those indicate times when we had human observers on site. And so from that, we determined that there were 13 precipitation events that happened during the field campaign. And so they're represented on this plot here. And so the size of the dot relates to the duration of the storm. The color of the dot indicates whether it was mixed rain or snow at Fortress Power Line. And then the location of the dot on the plot represents how much precipitation occurred at Nipika and how much precipitation occurred at Fortress. So something you can see quickly here is we had a lot of small events at Nipika that resulted in varying amounts of precipitation at Fortress. And there were very few large events at Nipika. And then just going into an example of some of our events, number 1 right here, that was our longest event. It was 65 hours long. It was from the 16th to the 18th of May, and it resulted in 12.3 millimeters of rain at Nipika and 20.2 millimeters of snow at Fortress Power Line. And then number 2 right here, That was our largest event by far at Fortress Powerline and Nipika. And we call this one our summer solstice storm. It occurred on the 21st of June last year. And I'll be going into more detail about that storm further on in the presentation. So here we have some plots that were created using data from the micro rain radar, and they're the average spectral reflectivity throughout the entire field campaign. The left panel is Nipika and the right panel is Fortress Powerline. And so just some background information here. A typical fall speed for snow is between 0 and 2.5 meters per second. And for rain, it's between 5 to 8 meters per second. So when you look at the Nipika panel right here, you can see the highest reflectivities are between that 5 to 8 meters per second. So this indicates that there was mainly rain that occurred at Nipika. And then when you look at Fortress, you see the highest reflectivity values in that kind of those snow velocities. So between that 0 and 2.5. So there was mainly snow at Fortress Powerline. However, you also see some moderate reflectivities in that kind of those rain velocities as well. So there was a bit of a mixture at Fortress Powerline. And then we see similar results when we look at some plots from the optical distrometer. So these pink lines here, this peak is from Nipika, and you can see again, it's within those typical rain velocity fall speeds. And so there was mainly rain at Nipika. And then at Fortress, you see this peak in the black bars, and it was mainly rain. However, you do see some smaller peaks here. Or sorry, so it was mainly snow at Fortress Powerline, and you do see some smaller peaks in that rain region. And then Fortress Junction is represented by these gray bars, and you can see two distinct peaks. And so it received a mix of both rain and snow, almost even. And then just further subdividing that into the type of precipitation, we can see Nipika, almost completely rain. Fortress received the most graupel and wet snow, and then Fortress Junction received the most rain and graupel and wet snow. And so now we're going into an example of one of our precipitation events. It occurred from 3:30 to 23:40 UTC on June 21st, 2019. The average temperature at Nipika was 6.7, and it was 1.6 degrees Celsius at Fortress Powerline. And then precipitation accumulation was 19 millimeters at Nipika, and it was 57.8 millimeters at Fortress Powerline. And this 57.8 millimeters here represents 27% of the total amount of precipitation that was received over the entire field campaign at Fortress Powerline. So it was a big one. And we have this plot here that was created using data from ERA5. And these red dots are our field sites on either side of the continental divide. And so you can see here that there's a lot of moisture available for precipitation, and that the flow is perpendicular to the continental divide. So this is a classic upslope event with moisture coming from the prairies and then flowing up and over the continental divide. And so again, we have spectral reflectivity plots created with data from the MRR, and these are only for this particular precipitation event. And so when we look at these reflectivity values, we see that Nipika received a lot of rain, whereas at Fortress received precipitation mainly, as well as some rain. A couple things to note about this Fortress Powerline plot here is these negative values indicate that there was upward movement, which leads to increased accretion. And then you see these really high values here. These can be disregarded. They're a mirror effect. And as we work more with these data, they will be processed out. And so then we have some spectrum plots using data from the optical distrometer and using the relation between the diameter of the particles and the fall speed to determine the type of precipitation. So all the particles that fall along this green curve here are rain. And so once again, we can see that Nipika received almost completely rain. Whereas at Fortress, you can see that rain occurred in addition to snow pellets, which are along this black line, and wet snow, which are along this red line. And then the color indicates how many particles fell. And then this is an example of one of our microphotographs. It was taken at 8:30 UTC on June 21st, and it's an example of a heavily rimed irregular particle. And so in summary, 13 storms were documented over the course of the field campaign. 4 were considered major, and 9 were minor. The eastern side of the divide was generally colder than the western side, and temperature was more variable on the western side. More precipitation occurred on the eastern side of the divide than on the western side by approximately 150 millimeters. Mainly rain occurred at Nipica, whereas snow, rain, and mixed precipitation occurred at Fortress Powerline. And then interestingly, precipitation never occurred on the western side of the continental divide when there was no precipitation on the eastern side. Thank you.
Thank you very much, Hilary. Great talk. Again, opening up the questions. And Nicholas has a question for us. Thank you, Nicholas. Interesting presentation, Hilary. What additional time series analyses have you applied to the data? Do you think that wavelet or time frequency analysis can provide insights related to precipitation phase partitioning and event occurrence?
So we're still in the process of analyzing a lot of the data right now. So we haven't done a whole lot further than what I've presented. We are currently analyzing the trajectories using data from the LiDAR. I didn't present any of the LiDAR data because it's taken us a long time to get it going. And so, yeah, I don't know if that answers your question, but I'm not sure what else we're planning on using at the moment.
Yeah, okay. Nicholas says thanks. A quick one from me. So who knew you could study precipitation in such detail? Eh?
Mm-hmm.
It's interesting in your scatter plot there that you have, it seems like all of the events occurred at both stations. Is that correct? I think your last conclusion related to this plot.
This one?
The plot where you show the bubbles with the different radiuses. That implies that every event happened at both stations, right, or not?
Well, you can see we have a number of dots like these 2 down here that are sitting right at that 0.
Okay.
So we saw this blue one here, maybe 5 millimeters of precipitation at Fortress, but 0 at Nipica. We used the data from Fortress to determine whether we had a storm or not, because there was so much more precipitation that occurred at Fortress than occurred at Nipica. We also, just anecdotally, as we were monitoring the conditions, we saw a lot of virga at Nipica. And that could be due to the different elevations of the stations of our field sites.
Great. Are there any other questions for Hilary? Well, a simple question. I just missed how did you measure your accumulated precipitation?
At our Fortress sites, we used a pluvio, or we had 2 pluvios at the Fortress sites. And then at the Nipica site, we had a Geonor.
Okay, so were there any issues with the pluvio not being able to pick up snow?
Not that we're aware of. The pluvio was very good at picking up the snow as far as we know.
Okay. All right then. Well, thank you very much, Hilary. We'll keep moving forward. So the final presenter today is David Olefeldt, who's from the University of Alberta and is working on hydrologic response to forest change. So if you're there, David, hopefully you can take control.
All right. How does it look?
It looks, well, not quite in full screen. Yes, that's great.
All right. Well, thanks for inviting me, and thanks for everybody who's hanging around a Friday afternoon to take a deep dive into the wonderful world of dissolved organic matter. So the study here today is led by Julia Orlova, who is a PhD student here at University of Alberta. And as you can see, it has a large number of co-authors here. And as you see from the title, we're looking at variability of dissolved organic matter across Canadian ecozones. So we have lots of collaborators who's been sending us samples throughout last year from different parts of Canada. And also a shout out to Fariba and Monica at Waterloo, who's been helping us do some of the analysis for water treatability, and to Ryan Hutchins, who's done some of the DOM analysis for the FTICRMS that we'll get to. So the project here is within the NSERC 4 water network. And the mandate of the 4 water network is really to look at delivery of drinking water from forested catchments across Canada. And it's a large number of Canadians who receive their drinking water from forested catchments. Some examples here. On the left image, we have, sorry, is my mouse visible? Can that be shown?
Yes, it's visible.
Okay, good. So that's Halifax with its water supply, its forested catchment right outside town. The middle picture here is a remote community in central Alberta that takes its water from one of the streams here. And the picture on the right is part of the Comox watershed out in BC. So one of the things that you see, of course, immediately here is that forested watersheds can supply water with very different water quality, from the dark, murkier water on the boreal plains of Alberta to the clear water of the more steeper areas in BC, right? And the color here is the dissolved organic matter, and that's what we'll focus on today. So dissolved organic matter matters. It has several ecosystem functions that it does in aquatic ecosystem. It controls much of the greenhouse gas exchange as the DOM is mineralized and turned into greenhouse gases. It's also an energy substrate that works its way through microbial food web and into the regular aquatic food web. And much of the biomass of food webs can be derived from terrestrial DOM in these type of aquatic ecosystems. It also determines the habitat by how far you can see in sight lines for larger animals. And then, of course, there are consequences from a drinking water perspective, where while not generally toxic in itself, it's one of the more costly to remove in the drinking treatment process. And if you don't remove all of it and you add chlorine, then you risk creating disinfectant byproducts that are carcinogenic, and you can also have buildup of microbial activity in your delivery system, right? So being able to treat dissolved organic matter is a key consideration. From the catchment perspective that we have, though, one of the reasons why we want to understand dissolved organic matter is, of course, we have disturbances and land use on these catchments, forestry being a large one, but also natural disturbances associated with climate change like wildfire or peat harvesting. And all of these may have implications for either the quantity or the quality of the dissolved organic matter that moves downstream. So for this project, our objective was to assess variability of stream DOM across Canada, across our forested ecozones. So we had collaborators at already established watersheds send us 2 to 6 samples from 2 to 6 streams from each one of these sites a few times over last year. We're looking at the variability within and between regions, and also variability within each stream right over time. And we're looking to link some of that variability to differences in climate, topography, superficial geology, and then later on also to link it to these water treatment indices. So here are where we got samples from. So we had actually 3 sites out in the Pacific Maritime that sent us, and then we have the mountain Cordillera, the Boreal Plains, and the Taiga Plains, Tukey Lakes on the Boreal Shields, and then around Halifax from there, the water that feeds Halifax. So just to get us started, to set the scene, we have our general water chemistry. We ran it through a PCA, and some of the things that come out is that the Atlantic Maritime and some of the Pacific Maritime here are associated with chloride, showing that it's got an oceanic influence. We have something like the boreal shield and the other parts of the Pacific Maritime here, the purple, which is on igneous rock with thin soils where we don't have not a lot of weathering and not a lot of organic to move through. We have mostly dilute water overall. We have the sedimentary bedrock of the mountain Cordillera up here, lots of calcium, also nitrate for some reason. And then we have the two big blobs here, which is the plains and the taiga and the boreal plains, which have the greatest variability, partly because we have so variable and heterogeneous superficial geology in terms of sands and clays and lots of peatlands that creates often high concentrations. And there you can see as well, it's associated with the dissolved organic carbon and nitrogen, which is in the DOM, right? So that's the link. So we want to look at the quantity then of DOM, or here as in the carbon aspect of it. We have the highest in the boreal plains and the taiga plains, followed by the Atlantic Maritime, and then we have a boreal shield in the Pacific in one of them, and then the really low concentration in the mountain Cordillera and some of the other more steep ones along the Pacific Maritime. So this is more than an order of magnitude in variability and concentration, quite a bit more actually. But we also want to look at the chemical composition of this DOM, and there are many ways of looking at it. Of course, there are such a wide variety of molecules in what's the dissolved organic matter that anything that you measure usually looks at functional groups of the DOM. And you can do that with different levels of specificity, and you can do it in different levels of complexity of the analysis. So some of the simplest ones are based on absorbance. So absorbance has different wavelengths associated with particularly aromatic DOC, for example, rather than the more aliphatic. We can also start looking at fluorescence, either in simpler indices, which we have, or you can look at the full spectra and deconvolute that as a parafac analysis, which Julia has done, but we haven't quite finished that one, so we're not going to be showing the parafac here. We will be showing, though, the Fourier transformation ion cyclotron resonance mass spec. So this is a way of looking at molecular weight of individual molecules, and then you collapse that information often into something that's more graspable, which is this Van Crevelen diagram, where we now have the oxygen to carbon ratio on this one, and then the hydrogen to carbon ratio on the y-axis. And within here, you have different regions that are associated with specific types of DOM. So derived from condensed aromatics, lignins, tannins, carbohydrates, proteins, or lipids that have different functions in aquatic ecosystems. So now we put that into PCA. So we have all these indices of DOM quality. So all of these are what I would think of as concentration independent. So if you were to dilute the sample X number of times, it would still have the same measure. So it's only giving us an indication of relative abundance of certain types of DOM molecules. And we have most of the variability here on the first axis. And the ones we see here, we can see which indices here that are associated with it. So we have one of our simpler ones is a specific UV absorbance, which tells us how aromatic the DOC is. Also the humidification index, which is a fluorescence that tells us how reworked the DOM is, and also the polyphenols and condensed aromatics. All of these together really indicate that this is terrestrial derived and highly reworked by microbial activity. And that is very associated with the red here, with the Atlantic Maritime. And on the polar opposite, on the other side, we have the montane Cordillera, which is associated with higher BICs and H2C ratios and aliphatics. And all of these are more indicative of protein-like or microbially derived or deeper groundwater reworked DOM. We have then in our purple to turquoise is the Pacific Maritime again. So they straddle this whole range of the first axis from the more aliphatic to the more aromatic. But it then is different from the plains on the second axis. And the second axis is a bit harder to interpret. We have the E2, E3, and the S275, 295. Both of these are indicating that these are smaller molecules. And then possibly the OC ratio over in this direction indicates that it's more tannin derived. One way of interpreting this is that these tannins are wetland derived DOM, and possibly these smaller molecules may indicate more photodegradation that breaks apart molecules. Given that the plains have much more wetlands and it's a drier region with long residence time and water moving slowly, compare that to the really high precipitation, steeper, low wetland Pacific Maritime that is on the other axis of the PC2. And then in the middle there, we have the boreal shield, which suits it geographically as well, I suppose. We can also then look at the quantity and that DOM quality at the same time. So I'm using now the SUVA, which is the measure that was associated with the first axis very well here, and it's a very simple one to measure. And often it's assumed that if you have higher concentration, that should indicate that more of the DOC is terrestrially derived and more humified. But this graph really shows quite nicely that there are variability within that. So you can have something like the Atlantic Maritime and the boreal plains having roughly similar DOC concentrations, but very different quality. And the same of these mid-size concentrations of carbon, the shield and the Pacific Maritime also vary in terms of their quality. The last thing here to look at are individual streams. So these are streams now, I've connected the ones that we sampled several times over the year. And you can see that individual streams can have quite a bit of variability given whether it's high flow or low flow. And that variability for individual streams can be sort of the same amount of magnitude as the variability within the region, but much smaller than the variability between our regions. So now linking that to disinfectant byproduct formation potential, we find though that this is the formation potential. So this is the unwanted molecules after chlorination, and it is primarily linked to the quantity of our aromatic carbon. So not the aromaticity, which is the percentage aromatic to non-aromatic, but instead the total amount of aromatic DOC. The only thing that we found could actually increase our predictive capability for DBP formation potential is concentration of total nitrogen, which also has a positive influence on the formation potential. Adding these other more detailed DOM composition indices from the FTICR or the fluorescence did not help us very much in order to predict from DBP formation potential. Wrapping this up, we conclude that we have significant differences in DOM quantity, but also chemical composition between our ecozones. We find that these simple indices like SUVA, for example, can capture most of the variability between ecozones, but some of the FTICR MS data really provide some additional information that can help tease apart some of those regional characteristics of the DOM. We also found that in terms of predicting the DBP formation potential, it really was the quantity of aromatic carbon, and that these more detailed DOM indices are of lesser importance. And then the last one here is thinking about the use of a study like this and tying it back into land disturbances. So now knowing that envelope of variability both within and between ecozones of Canada can help you put an impact of a land use disturbance into context, right? Whether it is should we consider the impact on DOM from forestry as a large or a small impact, it can help to compare with the variability within and across these ecozones. And with that, I'd just like to, I have my last slide. Thank all the funders for the NSERC 4Water project. Thanks.
All right, thank you very much, David. I'll open it up again for questions, and we have a question here from Colin McCarter. Interesting talk. I might have missed it, but was the stream order considered? Could or did this help explain some of the variability in DOM characteristics?
Yes, so of course, since we were requesting samples to be sent to us from already established watershed observatories, there was a substantial difference in catchment size for some of these streams, where, for example, the Boreal Shield sampled very small catchments, and the Taiga Plains had the largest ones. We did include it in some of our analysis, and it had limited influence on our results, though. So I do very much think that the catchment size and stream order, and whether there are large lakes, for example, in your catchment, will have a large influence on the DOM. It did not come out in this analysis as one of the overriding influences. So it seems like the regional variability is stronger than that influence of stream size or lake reprocessing.
Okay, thanks. Are there any other questions? This is probably a simple question, but in terms of the quantity of DOM, why was it so high in the Boreal Plain?
It is an area which has very widespread peatlands, and that gives a very immediate connection between the organic soils and the water that goes through an organic soil and enters a stream network. And it's something that's known from boreal catchments, not just in Canada, that the more peatlands you have, often your concentrations of carbon go up. When you're in a forest, a non-peatland forest, much of the water is routed through a mineral soil, and the DOM that is leached from near the surface gets reabsorbed onto the mineral substrate and therefore gets filtered out before that water enters streams.
I see. Because I always think of the Boreal Plains as being a relatively low productivity compared to some of the other forests. But it's the peatlands that dominate the DOM, so.
I would say so, yes. It probably is a slightly lower productivity than some of the other areas here, but yeah.
Okay, well, are there any other last questions? It doesn't look like there are. Well, we've made really good time, and so I will draw the proceedings to an end now. And I would like to thank again the 5 speakers, really excellent talks today, and I really enjoyed it. And I hope you'll all consider joining again for the next session. I'm not actually sure if it's next week, but watch your emails and watch Twitter, and we'll have a few more of these really interesting sessions over the summer. So with that, I'll draw proceedings to a close. Thank you very much, everybody, for joining.